Swayam Prabha. Digital India. Educated India.
So, welcome back. Today we will try to represent basically the vectors and uh, therefore basically the phasors as complex numbers. So, advantage of this would be, this is our goal, and advantage of this is that it will allow us to do a complex number arithmetic with vectors. So, even the cumbersomeness that is associated with the parallelogram law of identities is going to be avoided. Also, by now it is very clear to us that because of the expressions like L di by dt, Vc is equal to C dVc by dV by dt, expressions like this, their representation in steady state, especially when we are dealing with additions and subtractions of vectors at the same frequency, becomes a bit difficult. So, I mean, just addition of two vectors or just addition of two phasors at same frequency, we can quickly put it onto vectors and do that. There is not much of a problem. But now, when they are going through these operations like differentiation or integration, and there is an amplification by omega when it is differentiated, or when it is scaled by 1 by omega when it is integrated, when such kind of things happen, and suppose these elements come in series or parallel or even a mix of series parallel circuits and so on, then how to handle these vectors properly with phase shift and so on and so forth gets cumbersome. I thought of trying to put some example for that, but even that I thought looks a bit difficult. So, it is probably easier now to take recourse to mapping vectors using complex numbers, the real part, the imaginary part, or the polar form. So, rectangular form or the polar form. For example, 1 plus I j 1, where j is the square root of minus 1, a complex number has real part of 1 and imaginary part is also. So, let this be the complex number, then its real part of C is also 1, and in this particular case its imaginary part is also 1. And if you had a complex number like 1 minus j 2, then its real part of is 1 and the imaginary part is minus 2. And if a plus j b is a complex number, these two being the real numbers, then a minus j b is called as the complex conjugate or if this is C, then it is represented as C star. So, these are some of the common thing that we do. Now, suppose you have 1 plus j 2 and 2 plus j 3 as two complex numbers, and if I ask you to add them, you add their real parts and you add their imaginary part. If I give you the same numbers and say ask you to take a subtraction of it, you subtract their real part and you subtract their imaginary part. If I ask you to, let us say, divide two complex numbers, then what do I do? First I take a complex conjugate of the denominator. So, I multiply it by 1 minus j 1 and this, and then the if a plus j b is a complex number, its complex conjugate, when you multiply by its complex conjugate, it is a plus j b into a minus j b, which is nothing but a square plus j times of b a minus j times of a b plus or rather minus of j square times of b square, I mean expanding this thing. So, b a, because the real number multiplication commutes, b a is equal to a b. So, this term goes to 0, and since j square is minus 1. So, minus of j square is going to be plus 1, j being the square root of minus 1. So, this will become a square plus b square. So, any time you have a complex number c, okay, and you multiply by its complex conjugate, then it is nothing but the square of the modulus of the complex number, which is the real part of c square plus imaginary part of c, again square of that. So, complex conjugate becomes like this, and if you multiply two complex numbers, let us say a plus j b and c plus j d, then basically there are two it is a 2 cross 2 multiplication. So, 4 terms will arise like a c plus j b c plus j a d minus plus j square b d, which is same as saying that add the real parts together. So, a c j square being minus 1, this can be written as a c minus b d plus j times of b c plus of a d. So, the product of two complex numbers in general is going to be a complex number. Now, coming back to the division of it. So, suppose I do a plus j b divided by c plus of j d, then the correct way of doing this is to multiply first the denominator by its complex conjugate, which makes it c square plus d square, and again also the numerator by its complex conjugate, which is complex conjugate of c plus j d is c minus of j d, and then expand it. So, this will become a c plus b d, because minus j square b d is plus of b d, plus j times of b c minus of a d divided by c square plus d square, which is nothing but a c plus b d divided by c square plus d square plus j times of b c minus a d divided by c square plus d square, which basically shows that it is also another complex number. So, product of two complex numbers is a complex number in general, division of two complex numbers is a complex number in general, addition and subtraction of two complex numbers is a complex number, 0 is essentially 0 plus j 0. So, when I add 0 to a complex number, it is again the same complex number. Same way, when I subtract 0 from a complex number, it is again the same complex number, and a real number 1 can be written as 1 plus j 0, and when I multiply this by 1 plus j 0, then I am going to basically get again the same complex number. I leave it to you to simply verify. And so therefore, the 0 element from the real numbers and the identity element from the real numbers carries forward to the complex number. If alpha is some real number and I scale this complex number by alpha, then it is going to be a alpha plus j times of b alpha, and if I divide it by alpha, provided alpha is not equal to 0, then it is a by alpha plus j times of b by alpha. So, these are some of the standard arithmetic operations that we do with complex numbers. I am sure all of you are conversant with this from your high school days, and these are what we are going to now use. These are used in electrical engineering extensively. This form is known as rectangular coordinates, and there is alternate form which is known as polar coordinates, which we will come very soon to. So, both these forms are used extensively in electrical engineering to represent phasors, impedances, admittances and so on. So, why are we learning complex numbers right now? Because of their role in representing phasors, impedances and admittances. So, that is why we need to get a good handle on the complex numbers. Now, we also want to now let me slightly one particular identity of interest to us is Euler's identity, and Euler's identity basically says that e to the power j times of theta is cos theta plus j sin theta. I want to get to the crux of this identity in more detail, because Euler's identity plays a very important role in again our understanding of electrical engineering, signal processing, many other places as well. This j, if you would have realized, I am writing under root of minus 1 as j, j square as minus 1, minus j square as 1. This is because in standard algebra books, rightfully imaginary number I is written as minus of under root of minus of 1. I indicates the first letter of the word imaginary, and it is shown by this. So, you get I square is equal to minus 1 minus I square is equal to 1, but electrical engineers prefer this electrical engineers refer as a complex imaginary number, unity imaginary number as j, simply because of the fact that I has already I is already reserved for representing current. So, we need some another symbol. So, we use j, the very next alphabet after I. So, this confusion sometimes create confusions when you as an electrical engineer talk with somebody in maths or something like that. You should first set this doubt to rest, that you are using j to represent minus of 1, because I is used for currents, and there is no other reason to invent a new There is no other reason to invent a new symbol or something like that, and then you have to move forward from there. Okay. Now, how does complex number, this must be bothering you probably this question, how does complex number connect to vectors? This is an interesting question that must be somewhere there at the back of your mind. How does this complex number connect to vectors? To understand this, first of all, let me go to even further fundamental definition of what is a exponential function. We know by and large we know exponential function is e to the power x, or in general a to the power x, where a is a constant. Now, we are in particular looking for a function, or rather a specific choice of a, such that when we take the derivative of this function, we should get the same function. This, what is that function whose derivative is itself? Is it, this is by itself a very interesting question in calculus, and that is the question. When we try to answer that question, we come to the answer that, cutting a long story short, that such a function is e to the power x. So, d by dx of e to the power of x is e to the power of x, and obviously integral of d to the power of dx is also e to the power of x. So, exponential function has a very fundamental property out of which it has come, which is that its derivative is itself. When you take the derivative of an exponential function, the same function reappears without undergoing any change, that is very important. Now, again jumping a bit, e to the power x can be represented by a series expansion like this. We need to show that this series converges for x real. We need to show that this series converges, otherwise it does not make sense, but we are not going to show here. I am going to take this identity as it is and accept that this we assume that we have studied that it converges. If you have not studied how it converges, I would suggest to you that you go through a proof and show that this series actually converges to a finite value when you take x to be finite. Now, assuming that this series is convergent, let us take the d by dx of e to the power of x. Then what is that going to be? The first term's derivative is 0, second term's derivative is 1, third term's derivative is going to be 2x by 2 factorial, then the third term is going to be x cube by 3 factorial. So, it will be 3 x square by 3 factorial, so on, n x to the power n minus 1 by n factorial, and so on. So, if you write this is 1 plus x, because 2 factorial is 2 only, and 3 factorial divided by 3 is 2 factorial. So, therefore, 2 factorial, and because n factorial is n into n minus 1 factorial. So, therefore, this is x n minus 1 by n minus 1 factorial. So, the next term is obviously going to be x to the power n by n factorial, and so on. So, which is basically again that same thing e to the power x, which we have defined here. So, therefore, we have come to a very important conclusion that yes, e to the power x function has this as its Taylor series expansion, and this has its Taylor series expansion, and you can actually this is a Taylor series expansion. If you recall Taylor series expansion, suppose I want to write x plus delta x and the function is continuously differentiable any number of times, then around x naught, then I will write it as f of x naught plus f dash of x naught times of delta x plus f double dash means taken twice derivative by 2 factorial into delta x square and so on up to nth factorial of x naught divided by n factorial into delta x to the power of n and so on. So, this is the Taylor series expansion of this. So, when we are looking at our series e to the power x whose basic definition is that its derivative is itself only. So, now take x naught as 0 and delta x as x, then f of 0 because it is of the form a to the power x and a not being non-zero, a to the power 0 is 1. So, therefore, the first term will be 1 plus f dash of x naught. So, it is again the derivative is the same thing. So, f of x naught, f dash of x naught is going to be same as f of x naught, which we have already calculated, written it as 1. So, it will become 1 plus delta x. Instead of delta x, I am going to substitute x. So, 1 times of x and then again take the derivative one more time. So, first derivative was f of x. So, when you take the second derivative again, derivative of again you are looking at derivative of f of x only. So, it is again f of x and again you evaluate it at 0. So, it is going to be 1. So, in general we can say that whatever be the n, this is going to be just f of x of naught and which is f of 0 which is 1. So, you will get the third term as 1 into x square by 2 factorial and so on 1 into x to the power n by 2 factorial and so on, which is same as 1 plus x square by 2 factorial and so on x to the power n by 2 factorial and n factorial by so x to the power n by n factorial and so on, which is exactly what I had written here, so to say out of memory lane straight away, but this is nothing but Taylor series expansion of expansion with basic definition of the function that its derivative is the same function itself. And so, a function like this, now if you evaluate it, so you want to, so let us call this a, whatever that a, let us call it as its value as the exponential function. So, we designate it by e and we want to find out what is e to the power 1 or in other words e. So, e to the power x is e to the power 1 means x is 1. So, then e value of that base e is going to be 1 plus substituting for x, let me write the third term also, 1 plus x cube will be again 1 by 3 factorial plus 1 by 4 factorial and so on. And so, you can see first 1 and 1 will give you 2 plus 1 by 2 factorial will give you 0.5 plus 1 by 3 factorial is 0.5 by 3 or 1 by 6. So, 1 by 6 is going to be 0.14. So, 6 6 are 36 and so you will get again 4 and so 0.166 plus 1 by 4 factorial is going to be 1 by 16 and I am not going to to calculate that, but okay, let me just put this last one term. So, you are going to divide it by 16. So, you put a point, then 0 and and another 0, and 16 6 are 96. So 4 and so on. So you will get something like 0.06 or so, and is it 1 by, is it 0.06 or 0.006? We will check it out, and so on. So you can see that this is 2.5 I'll just keep these many terms here, 2.5, 2.666, and there are so additional terms and so on. So, if you keep adding this, somewhere it comes close to 2.73, 2.73, and this is where it tends to converge, but this is a irrational number. The basic exponential is a irrational number, but it is somewhere between 2.5 and 3, somewhere like 2.73 or 2.666, 2.72 or 2.73, that is what it comes to. It is a irrational number. So, E is not like a rational number, it is not even an integer, it is not even a rational number. E is actually a irrational number, and that is, I think, quite understandable and acceptable that we are getting the value of E to be a irrational number, because what we have said is a very specific condition we have imposed on it, that e to the power x, the derivative, our basic requirement was that derivative of e to the power x should be equal to e to the power x. We wanted a power function which met this particular requirement, and we would have been extremely lucky if we would have got it as some number which is a rational number. We would have been extremely lucky. So, we have now got some handle on this series e to the power x. Now let us try to get, I am in a position to address Euler's identity. Now I am in a position to address Euler's identity. I am interested in e to the power j theta. So, now let us evaluate this e to the power x, which was 1 plus x square by 2 factorial and so on up to x to the power n by n factorial and so on. Let us take x to be equal to j theta and simplify this. Let us see what it comes out to be. We are now going to put j of theta is an imaginary number and theta is in radians. Of course, it is just a number for the sake of right now, but usually in radians, and now we write e plus j theta. So, x is j theta, j square theta square by 2 factorial plus j cube theta cube by 3 factorial plus j to the power 4 theta to the power 4 by 4 factorial and so on. Now, let us write it 1 plus j theta, j square being minus 1. So, this becomes minus theta square by 2 factorial, and j cube is j square is minus 1 into j. So, therefore, this third term is going to be minus of j theta cube by 3 factorial, and j square is minus 1, j to the power 4 is minus 1 square. So, therefore, it is plus 1. So, it is 4 factorial and so on, and so this can be written as 1 minus theta square by 2 factorial, but theta to the power 4 by 4 factorial plus of j times of theta minus theta cube by 3 factorial, and you will get plus theta to the power 5 by 5 factorial and so on. So, you will get a expansion like this, but this is nothing but the expansion of cos of theta. This is nothing but the expansion of cos of theta, and this is nothing but the expansion of sin of theta, and so you immediately come to this very fundamental identity, which is that e to the power j theta is equal to cos theta plus j theta. Now, just for the sake of completeness, because I usually like in the first course to set my maths proper, not assume too many things. Of course, I can't really start anything from ground zero level, that is simply not possible, but still I like to go as much back as possible, so that we do not feel gaps and we do not feel like we are picking something which we do not have enough understanding of and applying them straight away. So, when I say that cos theta of this is 1 minus theta square plus 2 factorial plus theta to the power 4 by 4 factorial and so on. So, let us just see how this comes from. Once you know how this has come from, you know how the sin theta series how the sin theta series would come out from. So, again write this as cos of 0 plus theta, and write the Taylor series expansion. So, this will be cos of 0 plus derivative of cos of theta, I will write it like this, evaluated at theta equal to 0 times theta by 1 factorial plus again 2 derivatives of cos of theta evaluated at theta at 0 times theta square by 2 factorial and so on. Let me just write this much only. And so, the first term cos of 0 is 1. What is the derivative of cos of theta? Minus sin theta. What is sin of 0? 0. So, therefore, there is no second term will not come into picture. So, then come to the third term. So, derivative of cos of theta is minus sin theta, take one more times derivative, it becomes minus cos of theta, evaluate it at theta equal to 0. So, it is minus of cos of theta will become minus of 1. So, therefore, minus theta square by 2 factorial, and then you can see that the sign toggles and no odd numbered term will come. So, again this thing comes from the Taylor series expansion, and if you know this and you know that derivative of cos of theta is minus of sin of theta. So, take the derivative on the right hand side. So, 0 minus 2 by 2 factorial into theta plus 4 by theta cube divided by 4 factorial and so on. So, therefore, minus of sin of theta will be equal to minus of theta minus theta cube by 3 factorial plus theta to the power 5 by 4 factorial, and therefore, sin of theta will be theta minus theta cube by 3 factorial plus theta to the power 5 factorial and so on. So, everything on this Euler's identity, so to say, is resolved for us. There is nothing mysterious around it. So, now that we know that e to the power j theta is cos of theta plus j sin of theta, we can say that e to the power minus j of theta is cos of theta minus, because cos of minus theta is cos of theta plus j times sin of minus theta, but sin of minus theta is minus sin theta. So, therefore, this is cos of theta minus j sin of theta, and so add the two, you will get cos of 2 cos of theta is e to the power j theta plus e to the power minus j theta, or cos of theta is e to the power j theta plus e to the power minus j theta by 2. Similarly, sin of theta you can show that it is e to the power minus j sin of theta by 2j. So, you can actually get cos theta and sin theta from the complex exponential. So, this e to the power j theta is actually called as a complex exponential. Now that you have a complex exponential, an interesting question for you to ask is, what is d by d? Can I take a derivative of complex exponential with respect to theta, which is a real number? And so, you are looking at d by d theta of cos of theta plus j times of sin of theta, but derivative of cos of theta is minus sin of theta and derivative of sin of theta is cos of theta, but minus 1 can be written as j square sin of minus of j, minus 1 can be written as j square. So, you are writing this as j square sin of theta plus j cos of theta. So, now take j as common. So, this becomes j times of cos of theta plus j times of sin of theta, but cos of theta plus j to the power sin of theta is e to the power j theta. So, therefore, d by d theta of e to the power j theta is j times of e to the power of j theta. Now, suppose that theta is omega t. Suppose that theta is omega t, then d by, and we will have many times to take the derivative of e to the power j omega t by dt, then a very simple chain rule application tells you that this should be equal to e to the power j omega into e to the power j omega of t. That is, chain rule application here is the e to the power this by this is this times e to the power this times d of t, but this is j e to the power j omega t into the second term is omega. So, it is j omega e to the power j omega of t. So, this identity is this identity is very crucial for us. This identity is very crucial for us, and we are going to use it again and again in this particular course. So, now you can write cos of omega t as e to the power j omega t plus e to the power minus j omega t by 2 and sin of omega t as e to the power j omega t minus e to the power sin of omega t by 2j. So, now when I have a linear circuit, a linear RLC circuit, like I had a series RLC circuit, if you remember, and I was giving it, let us say, excitation of cos of omega of t. Now, if I want to solve this same equation, steady state response, I am only interested in steady state response in this course. So, if I am trying to get the steady state response, one way of approaching this would be to look at the response, evaluate the response to an complex exponential and then just look at, though the response will also be a complex. So, whatever that I of t will be actually a complex function, I of t will be a complex function, and then just look at the real part of it. Why? Because e to the power j omega t is cos of omega t plus j sin of, coming back, e to the power j omega t is cos of omega t plus j to the power plus j sin of omega t. So, if you have a response to this complex exponential and if you just look at its response, real part of it, you will get the response corresponding to cos of omega t as the excitation function. Let me put it this way. Let us say R I c of t plus L d I c by d t plus 1 by c minus integral to t I of tau d of tau is equal to, is the response to say cos of omega of t, and let us say that response to the sine function is denoted by I of s this is the response to sine of omega of t. So, now I am going to multiply this second equation by into j and add it to the first equation. So, then what will I get? I will get R times I c plus j I s plus L times d by dt of I c plus j I s plus 1 by c of minus infinity to t I c of tau plus j times I s of tau times of d tau to be equal to cos of omega t plus j times of sine of omega t, and this, but this is the response to the this right hand side. Now, the excitation function is the exponential function. So, therefore, this I c plus j I s is essentially the response to the complex exponential function. This is the complex exponential function of t. So, that is exactly the point. This whole thing is working because of the concept of linear circuits, that we are able to work this. The principle of linearity is what is allowing us to do this nice simple operations. But what I want to therefore say, wanted to tell you therefore is, we will work it round the other way. We first take the response to the complex exponential and then just look at the responses real part. So, the real part of is the I c of t. So, if your excitation function is cos of omega t, then just look at this and you will get the response corresponding to cos of omega t. If your excitation function was sine of omega t, then because that is imaginary part of this. So, therefore, just look at the imaginary part of the response and you will get the response for the sine excitation function. So, suppose that response to complex exponentials is easier to do than if it turns out that it is much more easier to manipulate, then responses to cos and sine will be much more easier. Now, the next question that would come to your mind is, but many times I have something like a cos of omega t plus phi as my excitation function, or b sine of omega t plus, or a sine of omega t plus psi plus phi as my excitation function. So, what do I do in that case? So, in that case, you look at e to the power the exponential as e to the power j omega t plus phi. You look at this function and now write this as a into j to the power phi into a into into j to the power omega of t, but this is nothing but a bar times of a bar times of e to the power of j omega of t. So, now if you look at its complex conjugate, then it is a into minus of j omega t plus of phi. So, this is a into e to the power minus j phi into a into e to the power of minus j omega t, or in other words this a bar star times e to the power minus of j omega of t, and cos of omega t plus phi is nothing but e to the power j times of omega t plus phi plus e to the power minus of j omega t plus phi by 2. So, therefore, it is a into e to the power j omega t plus a star into e to the power minus of j omega t by 2 and so on. So, once so therefore, all we need to do is basically take and so I mean what really I wanted to say is, though I said something else, since this is cos of omega t plus phi plus j times of sin of omega t plus phi. If I want to get a response to say a times of cos of omega t plus phi, if this is the excitation function, then I should just look at the real part of take this as my excitation function. Take this as my excitation function and look at the responses real part. But if I know the response to e to the power of j omega of t, if I know the response to e to the power j of omega of t, let us say this is I x p of t, then if I multiply this by a bar is that complex number a into e to the power of j of phi, then I will get the response here as the corresponding response will be a bar of I e x p of t, and then I take the real part of this and the real part of this, I will get the response to a to the power a into a response to e to the power cos of omega t plus phi. So, therefore, we are building up the base to calculate the response now to complex sinusoid. We are building up the base to solve responses to sinusoidal and sinusoids and cosinusoids through complex exponentials. So, let us now say that my excitation function, I want to solve the circuit R of I plus L di by dt plus 1 by C minus of when it is excited by e to the power j omega t. Suppose I want to get the steady state response to this function. So, what I will now do is I am going to first of all assume that because a complex exponential when we take its derivative, it is some constant, imaginary number j omega times again e to the power j omega t, and similarly when I integrate the complex exponential e to the power j omega t, therefore, it is 1 by j omega into e to the power j omega t. So, using this fact, I am going to hypothesize that the response is some a times of e to the power j omega of t, and let me now try to find out what this a is and what this j is. So, what we will now do is substitute this hypothesis, we will substitute this hypothesis here and see and equate it on the right hand side to e to the power j omega t and see what we get. So, what we get is r of r time into a to the power j omega t plus L times a j omega e to the power j omega t, because if I take d by dt of this term, a is a constant, I do not have to do anything. So, I will have to look at d by dt of this term, but then the j omega will come out again as common and same term will repeat. And similarly, for the last one I will get j omega in the denominator, a times e to the power j omega t should be equal to e to the power of j omega of t. So, now let us take a outside, a times of e to the power j omega t outside, and I will get this as r plus j omega L minus, or rather plus 1 by j omega of c is equal to e to the power j omega of t. And so, now I can cancel this and this, and I will get therefore, that a should be equal to 1 by r plus j omega L plus 1 by j omega c. So, if I give once this a has turned out to be a complex number, this a has turned out to be a complex number, and if you multiply 1 by j omega c both numerator and denominator by j, then and the denominator the j square will become minus 1. So, therefore, this can be written as 1 plus j omega L minus 1 by omega c. In other words, this is going to be minus of j by omega of c. So, this is going to be something like this, whose magnitude is a number that we have already seen, a number that we have already seen earlier. Is it not? So, this is 1 by z. So, what we did in the previous class is coming back to coming back to us. The response to, so suppose I gave V m e to the power j omega t as my complex exponential, my response I will be, I of t will be V m divided by under root of, my response is going to be first of all I will write I will have a complex number I bar, which is written as V m divided by, now I will call this as impedance z, where z is a complex number of the type So, the response is going, so I first calculate this I bar, and now the response, complex exponential response is going to be simply this. So, if my excitation was V m cos of omega of t, then I just need to look at the real part of this to get the steady state response, and if my excitation function was V m sin of omega t, then I just need to look at the imaginary part of this to get the steady state response. So, things are getting simpler, though they may still look to you as bit indirect. When I in the next class I will come back to solving some numericals and questions and so on. You will see that at the end of the day it has turned out to be a beautiful piece of simple equipment which you can handle with ease. So, the important thing to realize is this j omega L is called as the inductive reactance unit ohm. Why? Because j is a dimensionless quantity, it is square root of -1, and 1 by j omega c or minus j by omega c is called as the capacitive reactance again in omega. And if I have a R, L and C which is excited by a sinusoid. So, I show a circle and just a sinusoidal function inside of it, and I am just going to write it as V bar. So, V bar means if cos of omega t is of reference, it is of this type. If sine is of reference, then it is of this type. Frequency of course is always fixed. Then its response is going to be some I bar, some I bar. So, right now it is right now you can take the V bar to be, when I write it as V bar, you can take it as a complex exponential V bar into e to the power j omega t, which is some magnitude V times j to the power phi e to the power j omega t. And so, this is V bar e to the power of j omega t plus phi and so on. Again this polar notation I will be connecting a bit more in the next class. Then what you are saying now is this I bar, the response to it is essentially V bar divided by, this is V bar, right, V bar divided by R plus j omega L by omega c, which is V bar by the complex impedance Z. So, we are getting now towards Ohm's law in complex exponentials. So, involving complex numbers, we are getting Ohm's law, and therefore, if the excitation is V to the power a j omega t, if this is the V of t, if this is the V of t, then the response is I of t, the response is this. If V of t is Vm cos of omega t plus phi, then the response is real part of this, and if the excitation is Vm sin of omega t plus phi, then the response is going to be just as simple as this. So, once you have got response to the complex exponential, you can actually get response to these simple functions like Vm cos of omega t sin cos of sin of cos of sin of Vm cos of omega t plus phi or Vm sin of omega t plus phi by just looking at the responses real part or the imaginary part. And really speaking, this is all operation that is involved. First, write this complex number V bar, which is basically magnitude of V, which I am taking it as Vm, which I am taking it as Vm times e to the power j phi. And I have got more to say about polar coordinates in the next class. I am running out of time now. So, I will call this as V bar, write the complex impedance here and just look at this ratio of two complex numbers. I get I bar, immediately I have got response to complex exponential, and if I am looking at response to cosine function, then I will look at its real part. If I am looking to response at sine function, then I will sinusoidal excitation, I will just look at the responses imaginary part. With this, we will we will stop here for today, we will continue this in the next class. Thank you.